Hi, I'm Kaden, and this is my lab video for the Physics 1001 Week 3 lab. So, in the lab, we were told we had to calculate the acceleration of an object due to gravity, and we could do this in any way we wanted to with any of the equipment that we could find in the room. So, quickly we got to work, and we found the following materials, as you can see on the right. We found a retort stand, we found a bit of string, found a weight, a protractor, some tape, a stopwatch, a ruler, and a pair of scissors. So using this equipment, we decided we could make like a pendulum kind of thing, and we could use that to calculate gravitational acceleration using the pendulum time period formula. So as you can see there, uh, that's the pendulum time period formula, and we were able to rearrange that to solve for g. So all we had to do was find those values of t and l, which were the period between the oscillations and the length between the mass and the fulcrum. So the initial setup was to have the weight dangling from the retort stand connected by a piece of string. And in our first test, this piece of string was 12 centimeters. So we just dropped the weight from an angle of about 20 degrees, and then we'd have a stopwatch running in the background, and we would video that, and we would record the time period between each time the weight went forward and back, and we called that our time period. But we found quickly that these periods were way too short, and they were pretty hard to measure. So I've got a short video here showing that. You can just see how quickly that moves. You know, that's like barely even a second in between each oscillation. So we found that was very, very hard to record. So instead, we decided we would change our setup to make the length of string a bit longer. So you can see here in this little diagram, we've got setup A, which is our initial one, with the shorter piece of string, and setup B, we changed the length to 49.75, so you know, over quadrupled the length of string. After changing the setup, it was much easier because the period between each string was much longer. So this was as a result of the weight having to travel a further distance now. And we ended up totally disregarding that first initial test we did, and we used all of the values from our second setup in our final calculation. So the uncertainty values in this experiment included any measurements made with a ruler, and the uncertainty with that one was give or take half a centimeter, and the other uncertainty value was our reaction time with the stopwatch. In the second test, we ended up clicking the button as we released the weight to make it easier to get a value, just a simple start finish, recording 15 oscillations or 15 periods. And with a little bit of research, we were able to find that the average human reaction time is between 0.2 and 0.25 seconds. So those were our uncertainties for our reaction time. So after doing these tests 6 times on that second setup, the average time for the period was 1.434 seconds, and the distance between the mass and fulcrum was that length of string, which was 49.75. And we placed these values into our equation to solve for g, into that equation that we had earlier, and our result was 9.551 meters per second squared. So we were taught in that same day how to calculate our uncertainty values. So we were told to simply take our minimum and maximum uncertainties of each of our uncertainty values, which in this experiment we had 2, our ruler and our reaction time. So what we did was we took our minimum uncertainty of our ruler and combined it with the maximum of the stopwatch to create our absolute maximum value, our absolute maximum uncertainty value, and then we did the same, you know, taking the maximum of the ruler and the minimum of the stopwatch to get the lowest possible value. So these are our final values. So once again, we have that our accepted value that we had, the 9.551. Then we've got both our maximum and our minimum. And if we take that minimum and subtract it from our maximum, we end up with a total uncertainty of 0.618. And our accepted value for G here is 9.8. So our calculated value for G was quite close, but obviously we didn't expect to be spot on with that one. Obviously, we couldn't be completely accurate with this test. It was kind of a bit of a in the moment fluke kind of experiment, but I think with a bit more preparation and more accurate materials or a more accurate method, we might be able to find a way to get a more accurate and precise value of G. So yeah, thank you for watching.